Welcome back to week 3, and in video 3 we will talk about humidity and dew point, and specifically what are they and how we measure them. So humidity can be a tricky thing. It has several different ways to express and several different meanings. So what is it? In simple terms, it's the amount of water vapor contained in the air. There's two things you can measure. Your book might call these slightly different things besides absolute humidity and relative humidity. Absolute humidity is the mass of water vapor in a given volume of air. This is very difficult to measure, however, so you don't usually see it reported in on weather websites or in the news. What you do see is relative humidity, and what this is a ratio of the mass of water vapor in a given volume of air to the mass of the vapor of that volume of air can hold at a given temperature. So it's all dependent on how much water vapor that air can hold at that temperature. So it can change. So you change the temperature of the air, you change the relative humidity, because you're changing how much that volume of air can actually hold. So you're comparing the two, what's there compared to what it can hold. This is much easier to measure and more meaningful in terms of us, our comfort, basically. If we have high humidity, it's really uncomfortable, especially in the summertime. High temperature, high humidity means very uncomfortable situations. And we'll talk about measurement and human comfort towards the end of this video. So relative humidity relates to vapor pressure. You'll see some information in your textbook about this. What vapor pressure is it's the force that water vapor molecules are exerting against the inside walls of a parcel of air. So if we say we took a isolated chunk of the air, maybe put it in a balloon or something, we have all these different water molecules. We have nitrogen, we have oxygen in our atmosphere, of carbon dioxide. So if in that parcel of air, as those molecules are moving around inside that parcel or that balloon, those water vapor molecules are putting pressure or force against the inside walls of that balloon. This is another way of expressing humidity, so you might see this as well. Basically, if you have a high vapor pressure, that means you have a large number of water molecules or water vapor molecules in that parcel of air. Low vapor pressure, small number of water vapor molecules, so less stuff to bounce around inside that balloon and cause that vapor pressure to change. Saturation vapor pressure, you'll see this in your book and in some readings. This is how much water vapor is necessary to make the air saturated at any time. So if you have saturated air, that means you have really, really high humidity and probably precip happening. So the details of relative humidity, like I said before, it's the ratio of the amount of water vapor in a given volume of air to how much water vapor that air can hold at a certain temperature. This changes when temperature changes. Relative humidity is easier to measure, and a change in relative humidity can be caused by changing the temperature of the air or how much water vapor is in that air. So we're going to do some calculations, or we could do some calculations. You guys are going to do this in lab, but you're going to be looking at the water vapor content and the water vapor capacity. You could also do this using vapor pressure as well, actual versus saturation. So there's two different ways of calculating it. So there's lots of different methods that can go into determining a number for this relative humidity. We're going to use some instruments in class to measure this. So to understand this a little bit better, we're going to do another simulation. So we're similar to the last one in the last video or 2 videos ago, but instead of an open container, we're going to put a lid on this container. So we have a container that has some air in it, has some water in it, has a lid on top of it. We can measure the temperature of the air in that container, and then we also have a microscope attached to see what's happening at that water level. So what are the molecules doing, how much condensation is happening, how much evaporation is happening. So you'll see these arrows changing inside depending on which is the dominant process happening. So the yellow is condensation, the green is going to be evaporation. So at this situation here, we're starting out at 10 degrees Celsius. Our absolute humidity is 8 grams per cubic centimeter. Our absolute humidity at saturation is 8 grams per cubic centimeter, and then our relative humidity is 100%. So basically, if I go back one slide here, we are doing this equation. We're dividing two numbers and multiplying it by 100. So we're dividing these two to get 100%. If we were to measure vapor pressure, we're at 13 bars. Saturation, vapor pressure, 13 bars. Relative humidity, 100%. See, we divide these two, multiply by 1,000, we get our relative humidity. So when we increase temperature in this scenario, we add some energy in, things are going to change. So we increase by about 15 degrees Celsius. We see our absolute humidity stays the same, where our absolute humidity at saturation changes. We go to 11. We divide these two numbers, multiply it by 1,000, we get a relative humidity of 72%. Same thing here. We see our vapor pressure numbers change, and we get a new percent of our relative humidity. So at this point, as the temperature is increased, we see that there's more evaporation happening. So we're taking water molecules from the water, we're evaporating them into the air, putting more molecules in that air. So we're increasing that vapor pressure and causing this change to happen. Now, when we continue this process, things come to a new equilibrium. If we let it continue, and we see our new absolute humidity is 11 for saturation, and so we get 100% for our relative humidity, and we have things stable again. So we have that evaporation continuing until our relative humidity is back to 100%. So if we start over again, and we do the opposite, we have a decrease in temperature. What happens? Well, let's see. We decrease our temperature to 5 degrees Celsius. Our absolute humidity is staying the same. Our absolute humidity at saturation is 5.2. Our relative humidity is 153%, way higher than 100%. So what happens? We get condensation. Our relative humidity is over 100, then we have that water starting to condense. It can form clouds, it can form rain, all sorts of good stuff. Any kind of precip or cloud. And then this process continues. We continue to have condensation occurring until our situation becomes stable at 100% relative humidity. So that's kind of an overview, kind of simulation of humidity. So when we have our temperature increase, we have more energy available, the air can hold more water, so we have evaporation occur. Temperature goes down, the air can't hold as much of that water vapor, so we have condensation happening. It's kind of a flip-flop there when you change the temperature. So temperature is a major factor when it comes to relative humidity. So shifting gears to dew point. Dew point is the temperature at which the air reaches 100% relative humidity. So this is the temperature at which this happens. So in this example here, I have a couple different things here. So when this happens, when dew point is reached, we can have dew, frost, fog, clouds, all form when air reaches a dew point. So that means you have 100% relative humidity and condensation happening. You see this on if you have a hot day, you have a glass of ice water, iced tea that has water, ice cubes in it, and you see condensation forming on the outside of that glass. Well, if you were to measure the temperature at which that condensation starts, that is your dew point. That's when that condensation begins. So in this image here, we've got a cloud up in the sky that has formed and precip falling. In that cloud, our temperature of the air in that cloud is 40 degrees Fahrenheit. Our dew point temperature is also 40 degrees Fahrenheit. And our relative humidity is 100%. So that means we have condensation happening. Now right below that, in where the rain's falling, some people think, oh, if it's raining, we have 100% relative humidity. That's not the case. It depends on the temperature of the air. So in this case here, we have higher temperature air. Our dew point temperature is a little bit lower. So our relative humidity is 84%, and we have rain falling, but we don't have 100% relative humidity because we don't have that rain is not forming right where we are. It's formed up in that cloud where that relative humidity was 100%. So when we observe relative humidity, this is actually pretty important to firefighting. A lot of firefighters will want to measure relative humidity and dew point to figure out how dry it is and how high the fire risk is. So here we can see our relative humidity in the southwest is pretty low, in the 5 to 15%, really, really low. Up in our neck of the woods, we have pretty high relative humidity, pretty wet up where we are. And then in the northwest or northeast, we have kind of middle of the road relative humidity as well. And then when we look at the dew point in these areas, we have our dew point temperature is pretty low. Down in the southwest, pretty dry, makes sense. And then up in our neck of the woods, a little bit higher, but we don't see anything off the charts too much. And look at up here in the northeast, we have a pretty low dew point, so it must have been pretty dry up there. So how does humidity and human comfort relate to one another? Well, if we have high humidity and high temperature, it's really, really uncomfortable. So think tropics, East Coast in the summertime. When your body starts to sweat when it's warmer, the process of that sweat evaporating off of your skin causes your body temperature to lower, because that evaporation process requires heat, and so it's pulling that heat away from your body to evaporate that water off of your skin. When we have a really high humidity, water does not want to evaporate into the air because there's no room for it. The air is already pretty close to saturated with water, so evaporation doesn't occur. Whereas if you're in a dry environment, we have a low humidity, water will evaporate readily off your skin and you'll be feeling nice and cool. When you're in a dry area, you don't necessarily notice that you're sweating because it's evaporating so fast, and it's really easy to become dehydrated. So when you're in a high humidity area where the temperature is pretty warm, the temperature is going to feel even hotter because you can't cool down and your body's starting to overheat. And that's what heat stroke and heat exhaustion, that's when those occur. So how do we measure humidity and dew point? We are going to use a few methods. Sling psychrometer, we have 2 thermometers in this apparatus. 2 thermometers. One of these thermometers has a bit of cotton on it that you get wet. One's dry. Take this apparatus, you twirl it over your head in a circle. Water evaporates off of the wet bulb, which is the thermometer that has the cotton attached. And we, depending on how fast that water evaporates, you're just going to change the temperature of that wet bulb, and then you're going to see a difference between the two. So once that occurs, you read your 2 temperatures off, the wet and the dry. You see a difference. You use a chart to determine what your relative humidity and dew point is. So you're determining how much water evaporates off of that wet bulb to determine how much can evaporate. So if you have a little evaporating, your temperature doesn't change very much. Whereas if you have a lot evaporate, you have your temperature change, and that means you have a low humidity because you can evaporate more water off of that wet bulb. So you also can use hygrometers. There's a couple different types. There's a hair hygrometer, basically. You have human hair, horse hair, strung up, and then as the relative humidity changes, the length of the hair changes. So it's a way of measuring. It's not as accurate as a psychrometer. You can also use electrical hygrometers. These use a carbon-coated plate. As water is absorbed, it changes the conductivity, and we can measure it that way. We can also use a dew point hygrometer to measure dew point, and this is by using a mirror and seeing how that mirror actually fogs up or not, to see how much dew forms and condenses on that surface. And these are can be automated systems as well, which is pretty neat. So that's humidity and dew point and how we measure them. We'll come back and talk about how it changes over time.